Good day, dear colleagues. I am glad to present you my report for the conference APHYS in Kiev City. And now we shall speak about multifractal analysis in problems of the applied physics. I have two my co-authors. They are Professor Leonid Chernogor and Andriy Onishchenko. The purposes of this study are, first, presenting the multifractal analysis methods to the researchers. Second, considering the multifractal analysis methods for signals and processes. Third, showing the peculiarities, advantages, and disadvantages of the existing multifractal analysis methods. And the last, attracting the attention of the researchers to the multifractal analysis methods. Now you see lecture plan, and let's start speaking about these problems. Well known that according to the nonlinear paradigm had been formulated by Professor Leonid Chernogor in 1970s, and we now know that processes in the open nonlinear dynamical systems appear to be very complex and diverse. In particular, they can be classified as short-time, nonlinear, ultra-wideband, and fractal, monofractal, and many fractals ones. Last year, we studying many things about multifractal analysis of such signals and processes. 1 year ago at this conference, we said about monofractal analysis and about monofractals. And now we shall considering multifractals and multifractal analysis. Well known that multifractal is a fractal which needs more than the one value of fractal dimension for their description. Multifractal is an inhomogeneous fractal. And in this time, monofractal is homogeneous fractal. The term multifractal had been proposed by Frisch and Parisi. These samples describes what is multifractal. Multifractal has some statistical properties which don't exist for monofractals. And these are inhomogeneous Cantor set, inhomogeneous Sierpinski gasket, and a multifractal which can be built on renormalization scheme. Well known that there are some different approaches to the multifractal describing. Now we consider only one of them. I mean traditional multifractal formalism or well-known P model. But you see, there are, for example, multifractal formalism by Chabra and Jensen. There is informational interpretation of multifractal formalism. Very interesting is L model of multifractal formalism and statistical description of multifractals. And there is Mandelbrot's approach, which known as Hölder analysis, is significantly differs from the traditional approach of Frisch-Parisi, I mean P model. And this is very interesting idea, but this idea is not the aim of this report. And now we consider traditional multifractal formalism as it was created by Frisch and Parisi. In bounds of this approach, well known as traditional multifractal formalism, a basic idea of this approach is taking into account statistical properties of fractal object. For monofractal, these statistical properties are not significant and no ways to describe them. But for multifractal approach, there is such idea how we can consider them. Statistical properties are understood in sense of covering of the deterministic fractal object with generalized spheres usage. And in this situation, we can count how many dots of fractal set are in 1 second and other this generalized sphere. And number of these dots describes only statistical properties of this object. And there is the way which can give us the method of describing these peculiarities. This idea starts with generalized statistical sum. And the expression you can see here. For example, for inhomogeneous Cantor set, this generalized statistical sum is given by this equation. On generalized statistical sum based to other characteristics of multifractal. I mean, generalized fractal dimension spectrum, known as the Rényi dimension spectrum 2, and it is given by such equation, where tau from Q is scaling exponent, which or it known as the mass index 2, and it given by this equation based on the statistical sum, or on generalized statistical sum Z. And consider generalized fractal dimension spectrum. For example, for inhomogeneous Cantor set, we can such expression for them, and the graphical view, the plot of this function, is given by this picture. It is important to point that for multifractals, which has many values of these generalized fractal dimensions, as can you see on this plot, there is so-called multifractal support. Multifractal support for inhomogeneous Cantor set, for example, is homogeneous Cantor set. And Hausdorff-Bezikovich dimension of this set, given by this relation, is namely the dimension of the multifractal support. Multifractal support of multifractal is the base on which constructed this multifractal. And this generalized fractal dimension spectrum, in case of considering this multifractal approach to the describing of monofractal, vanishes this spectrum from Q to one fixed value, and this fixed value is the Mandelbrot dimension. No Mandelbrot. Hausdorff-Bezikovich dimension of this homogeneous Cantor set. This idea was produced by Frisch and Parisi, and as we know now, there is two different ways to describe the set of dimensions which should be used by multi-fraction description. First of them, this is generalized fractal dimensions spectrum, and there is another approach which well known as multifractal spectrum function. And now I want to tell you about another characteristic which well known as information dimension. This information dimension in general can be estimated and for monofractals too. And now we can see that information dimension is one of cases of generalized dimensions. If parameter Q is equal to 1, we obtain namely information dimension. And for inhomogeneous Cantor set, for example, we have such expression. Another way, when Q is equal to 2 value, we obtain another dimension, correlation dimension. This dimension can be evaluated for monofractals too. And it is important to point that this dimension is another particular case of generalized spectrum which we consider above. And for inhomogeneous Cantor set, we can obtain such values of these characteristic parameters of this dimension. And now we can see correlation dimension is 0.4 and informational dimension is equal to 0.5, and the dimension of multifractal support, namely homogeneous Cantor set, is equal approximately 0.6. And now let's consider multifractal spectrum function. This and another way to describe multifractals, and as for me, this way is better than generalized fractal multifractal spectrum. Why? No, I can explain it, and let's consider what we have. The argument of this function is value alpha. Alpha is Hölder exponent of this construction. And you can see properties of the function f from alpha, named, as I said, multifractal spectrum function. And for monofractal, this value is equal to alpha. And in this way, we can see that this alpha is equal to the dimension of the multifractal support. For example, for inhomogeneous Cantor set, we can obtain analytical expression for multifractal spectrum function, but in parametric form. And now parameter is Q value. I mean, we have function f from alpha, but this is parametrical form of this function, and then f is function of alpha, which is in this way a function of Q value, when Q is parameter. Now we can see picture on which we can see characteristic form of this multifractal spectrum function. This function for multifractals can such form, and second derivation from this function is less than 0. In case of monofractal, this construction, this curve, collapsed to the one point, and this point can be located in such way, alpha, for example, alpha 0, when alpha 0 is equal to f from alpha 0, you can see. Now consider Legendre transforms. These transforms well known from thermodynamics, and it is some idea how these transforms can be used for multifractal analysis. There are two kinds of these transforms: direct transforms and reverse transforms. And these transforms connected function f alpha with scaling exponent tau from Q and Q value. Direct transform is given by first system, and the second by second system. On this slide, we can see main properties of multifractal spectrum function. And now let's consider which multifractal analysis methods exist from the investigation of signal on end processes. On this table, we can see many such methods, many such different methods. And now we consider results of the practical application of these methods of first two. Namely, I mean wavelet transform modular maxima method and multifractal detrended fluctuation analysis method. We analyzed two very interesting signals, which are signals of gravitational wave. Well known that first experimental registration of gravitational waves generated by binary black hole merger can be obtained in September 2015 year, and they will obtained on the Laser Interferometrical Gravitational Wave Observatory in United States, namely in Livingston and Hanford, and thus we have two signals. We can see there are some similar between if we comparing them one with another. And well known, the authors of this discovery, this colossal scientific discovery, have received the Nobel Prize of this year. And now let's consider multifractal properties of these signals. It is very interesting. These signals appear to be multifractal signals, not monofractal but multifractal. And method VTMM, wavelet transform modular maximum method, shows such two type of multifractal spectrum function. And now we can see the parameters of Hölder exponent is that we can say about this idea that both of these signals are multifractal signals. And it is very simple to see that these signals have multifractal characteristics which changes with time. These are non-stationary signals in the multifractal sense. And due to this idea, we can apply another method which is called as multifractal detrended fluctuation analysis method, which can ask the instrument to discover properties which changes with time. And in this case, we have signal realization with time, first panel, minimal value of Hölder spectrum alpha min, maximum value of Hölder exponent alpha max, width of the spectrum delta alpha, generalized Hurst exponent. It defines as the location of the spectrum maxima. This spectrum, as you can see, has one global maxima, and the location on the horizontal axis is given by this value, named as generalized Hurst exponent. And the last panel, we have classical Hurst exponent, which is given by monofractal analysis. As you can see, there are some difference between these two second values, and this is for Hanford signal. I mean, signal which was obtained in Hanford. Another signal obtained in Livingston has similar, some similar characteristics, and we are glad that we obtained multifractal characteristics and this signal. And as I can believe, we obtained some maybe very small property, but this is one suitable addition to the two results which obtained by American scientists about gravitational wave. And thus, we obtain that gravitational wave signals has multifractal properties, and they are multifractal. Another sample which we can consider, this is signal of magnetic storm, These are variations of geomagnetic field which will be investigated with multifractal analysis, and we obtain these results, and we show that these signals are multifractals too. And if you can see, this is a result of multifractal detrended fluctuation analysis. With red squares, we have the disturbances which covers in this signal for disturbances. On the wavelet time frequency plane, we can see time frequency portraits of these disturbances, 1, 2nd, 3rd, and 4th. And these are multifractal characteristics with time of these variations. And the last sample of applying of multifractal analysis, the sample which we can analyze, this is variations of geomagnetic field which were fixed during the earthquake in Turkey. This earthquake was very powerful, and we found that in last multifractal characteristics, and this last characteristics is dimension of multifractal support, dimension of multifractal support. In all another ways, it is equal to 1, as well as multifractal support of the signal is the curve which don't have any fractal properties, and the dimension of it is equal to 1. But in case when the multifractal process vanishes to monofractal process, we can see this decreasing of multifractal support dimension, and we obtain such interesting result, and we believe that idea can be considered as harbinger of earthquake. And before earthquake, the time of earthquake is shown by this line dashed. And in time, this was before approximately 13 minutes before this moment of earthquake. As for me, it's very interesting result and very promising in the solving of problem of finding of earthquake harbingers. And now, conclusions. Multifractal analysis methods seems to be useful and attractive for all researchers which investigate the signal and process in different origin. And now references on different papers and books, and the end of this report. Suddenly I was limited by time bounds for this report, and thank you for the attention, my dear colleagues. See you again.